Alright, back with part two. Back with part two of my review or technical discussion of the Yamaha A-S1100. I said in my earlier video that I was going to bring the amp into my workbench here and we cover the back panel and do some tests. I'm still going to do that, but that will be in part 3 or 4. Haven't had a chance to lift that 50-pound beast off my rack over there right now, so I thought I'd take this opportunity in part 2 just to discuss the technical aspects. So this is going to be all technical. If you're not interested in the technical aspects or explanations of the amp, and you just want to see more videos of it, then skip to part 3 here, because I'm not even going to show the amp in this part. Okay, so picking up where I left off, the amp topology. I had mentioned that, well, you're looking at a depiction from Yamaha's website, and what you're looking at is how they describe the amp's functionality. And in order to understand what's going on here, I want to backtrack to briefly discuss typical power amplifiers, because this is very atypical. But in brief, before we backtrack, is you're looking at a bipolar junction transistor driving an N-channel MOSFET, and here's the MOSFET's power supply right here. Now forget that side for now. Let's just look at one side, because it's called a balanced and symmetrical amp. The balanced part means that they're basically these two sides here are symmetrical. They're identical, and they create a bridge across the load, and that's the balanced part. And I can tell you that a positive, I shouldn't say positive, but the two sides, the two sides are fed with inverted signals. So that's, and so what each of these sides is doing is an inversion to the other side. But when there's no signal, the bridge is balanced right here. And then the signals unbalance the bridge and allow for the current flow through the load. It's floating because there's absolutely no connection to earth ground or even to chassis ground. Here, these power supplies are in the loop. There's the other power supply there. There's two of them. Are in the loop of each respective output transistor. There's no reference to ground at all. In fact, I've got to be very careful when I do tests of this, because I cannot use typical oscilloscope configuration, because the oscilloscope's probes are referenced to earth ground, and by plugging the alligator clip of the oscilloscope probe, by attaching that to parts of the circuit, you could short something out. You could damage the scope and the circuit. So the only way to really test this, you can use a digital voltmeter, battery powered, no problem, but the only way to test this is either with differential probes, which I don't have, they're very expensive, or with a battery powered oscilloscope, because there's the battery powered oscope, or a multimeter scope, has no reference to earth ground, and you can take differential measurements. That's a tangent. Okay, so looking at this circuit, each side of this circuit is its own amplifier. So, and they're identical. So one side of the circuit, here's the power supply. This MOSFET is fed by a signal and basically becomes a variable resistor and controls the signal flow through this loop right here. The other side, the other MOSFET, is fed by inverted version of the signal, and it will cause its current to flow in its own loop right there. And that configuration, and I'm going to get into more detail about that in a minute, that configuration is referred to as a Circuitron. And feedback, I should say, this is a pretty accurate diagram for a brief diagram. This is the input. This depicts the input signal right here, okay? And the input signal goes through a differential amplifier. That shows an op amp, but I can tell you the diff amps in the schematic are not op amps, they're discrete. Okay, so signal comes in, and even though it's poorly depicted, out of the differential amplifier you'll get inverted versions of the same waveform, and they come up and they feed these BJT drivers, which feed the MOSFETs. MOSFETs do their thing, and so you have identical but inverted versions of the signals in their own loops, with their own power supplies, basically going through the speaker in the polarity is opposite directions. So, for example, when I'm going to pick a sine wave right here, and this is the opposite right there. So, for example, when we're here and this, when this sine wave is at its peak, at the same time, this sine wave is at its peak negative, and this is at its peak positive. So you get a differential voltage, and you'll get current that flows. When there's no signal at all, none whatsoever, it's idling. And you can see that positive supply DC is there, and you can see that the positive supply DC is there. It's the same voltage on both sides of the load or the speaker, and no current flows. So the only time current flows is when you have a signal, and that's by virtue of the inverted polarities. Both MOSFET output transistors are of the same variety. They're both N-channel enhancement MOSFETs. Okay, so this is a very accurate. Now I'm going to get into the schematic diagram, the actual schematic diagram, in a minute, but before I get into it, I want to briefly cover the differences between the Circuitron, which is what this is, and your ordinary and customary amplifiers. And I'm not going to get highly technical here, just a broad overview. This is a typical, and I picked really simple diagrams from the web because there's no need to get into complicated schematics, but this is a simple Class A transistorized amplifier. And this, here's the load, so this would be the speaker, so to speak, even though this circuit wouldn't drive a speaker, it would need some help, but let's pretend it can. There's the load. And this transistor will conduct current in proportion actually to the current flow through it, but I'm going to draw a voltage signal there, and it will output an inverted version of it right there, and it will this transistor will conduct all phases of the sine wave through 180 degrees. I said 180 in the last video. I meant 360 degrees. There's 360 degrees of the sine wave all the way around to where it starts. So this transistor does all the work, all the amplifying, both negative and positive peaks of the sine wave. It does it all. That's a Class A. The transistor never turns off. It's always working. Okay, so now you're looking at a fairly typical, but this is an unsophisticated version, but a fairly typical Class AB or Class B. There's very little difference between Class AB and Class B. There's just one subtle difference, and that's class AB, these transistors are slightly biased into class A, but quickly pick up into class B. So here's what class B means. Okay, class B is when you have two different transistors, usually of the opposite polarity, NPN and PNP transistors, and they each share the workload. So when you get a positive going portion of the sine wave, this transistor is off, it's doing nothing, and this one is on and it's conducting 180 degrees of the sine wave. As soon as you enter into the negative portion of the sine wave, the opposite happens. This transistor is off and this transistor starts conducting for the final 180 degrees. So it's called a push-pull. This one pushes, that one pulls. And by choosing with a push-pull amp, I'm getting into too much detail, but if you don't bias them properly, you'll get what's called crossover distortion. And instead of getting a pure sine wave out where the two meet, okay, where this stops pushing and that starts pulling, you'll get a little blip there where they hand off to each other that is basically distortion. And to fix that crossover distortion, you have to do two things. You have to bias these transistors so they're always conducting a little bit. So you push them a little bit, each one a little bit into class A, and that will clean it up for the most part. But there's still always just a little bit because the two can't hand off to each other perfectly, and the transistor characteristics are different. One's a PNP, one's an NPN, and they all have manufacturing variances. So to eradicate the remaining crossover distortion, you have to have negative feedback. Okay, so negative feedback, basically, here's your amplifier, and you've got to feedback an inverted version of it. And you've got to add it to the original circuit, and it's an inverted version, and you add it because it's negative, it subtracts it from the input signal, basically. And there are many ways you can do that, but you have to rely on fairly heavy amounts of negative feedback to clean that up. And negative feedback has other benefits of improving the bandwidth, and there's some benefits of it, but there's also some drawbacks of it as well. But almost all amps need some negative feedback. But that is a class AB or class B push-pull. Very typical of almost every amplifier out there nowadays, except for the digital switching amplifiers are kind of in these days. That's a whole different concept. But now, here's a Circuitron. This is what the Yamaha is. And basically, it's two different circuits. Okay, this is your load right here. This is the loudspeaker. And here are the terminals to the loudspeaker. And so in this case, you've got a power supply. It's a battery. No, not a battery, but a power supply, positive and negative. And you've got a control device, in this case, a MOSFET. And when that MOSFET turns on, current will flow in a loop through the speaker. And again, you have a completely separate circuit down here with a separate power supply, and it's kind of the opposite. When this MOSFET turns on, you're going to get current flowing in the opposite direction through the load. So current flows in this direction. Pretend we're just dealing with DC for now instead of AC. And when this guy is on, current flows in that direction. If they're balanced, if the bridge, this is a bridge, if it's balanced, equal amounts of current will flow in both directions, and there'll be no voltage drop at all across the load, and hence no current through the load. The only time you can get current through the load is when the bridge becomes unbalanced. And to unbalance the bridge, that's why we need opposite phased AC signals. that will unbalance the bridge. And here's a depiction of an unbalanced bridge. Okay, so right here, pretend these are the transistors, and we're just going to depict them as current sources, because they are. So if this transistor is conducting such that 1.2 amps is flowing, okay, so we have 1.2 amps flowing in that loop like that. This one is conducting such that 1 amp is flowing in the loop like that. Well, if 1.2 amps is flowing into this node right here, and we know that 1 amp is flowing through this transistor, then where'd the other 200 milliamps go? It has to go somewhere. Well, it goes through the load, and there it is. And then you have the opposite scenario. So basically you have pushing and pulling, so to speak. Here's the opposite scenario where this guy is conducting 1.2 and he's conducting 1, and current flows in the opposite direction. And so that's how you get AC, by unbalancing the bridge. Again, when both of these, with no AC applied, and both of these transistors are idling at their quiescent point, equal amounts of current would flow. You have no voltage across the load, hence no current through the load. It's idling. You'll notice that these power supplies right here are not, there is no ground. There's no concept of a ground. There's no reference to a ground of any kind. These are two independent power supplies that powers its own loop, basically. So it's floating above ground, no reference to ground. It's called balanced because this is a bridge, and when there's no AC, when there's no signal, the bridge is balanced, there's no current. Yamaha mentions symmetrical. Well, symmetry is an inherent concept of the Circuitron. Of course it's symmetrical. It has to be for the bridge to be balanced. So now, Circuitrons are just not used anymore. Okay, this is they were used in some tube circuits, some transistor circuits of the 60s and 70s, maybe. It's just, but it's a very elegant way of doing things. To me, it's one of the more, just looking at how it works, it's simple, elegant, and it's one of the more, to me, it's one of the more pure ways of amplifying. Geez, if I had to choose all of the types of transistor amps to probably do a project and design from scratch myself, it would definitely be the Circuitron. It's really cool. There are some problems with it. Not really problems, but there are some inherent risks with this. And I won't get into all of them, but one of the main ones is this bridge has to be perfectly balanced at idling. If something goes wrong and a transistor dies or something, characteristics change and that bridge becomes unbalanced, you get DC running through your speakers, and that'll kill them. So you need some protection circuitry and some monitoring and some servoing to ensure that that bridge never gets unbalanced. And Yamaha, of course, has all that stuff. Very well protected. It's not going to happen in the Yamaha. Alright. Now, one more thing I want to say about MOSFETs, and then we're going to go to the Yamaha schematic. Alright, so clearly, well, not clear, this is kind of fuzzy, but Yamaha uses N-channel MOSFETs. And MOSFETs are the transistor equivalent to a vacuum tube pentode. Now, I have a triode here, but you can see with a triode amplifier, we've got a grid, a cathode, and a plate. And when this grid, now electrons are flying through the air from the negatively charged cathode to the positively charged grid. And there's a screen inside of there, it's a mesh screen, and when that grid changes its voltage, so for example, when that mesh screen goes positive, that positive voltage on the screen will repel the electrons, will attract the electrons, and more electrons will flow, increasing the current. When that grid goes negative, right here, well, the negative will want to repel the electrons and on the cathode and reduce the flow of current. So this is a voltage controlled current source. By changing the input voltage, you can change the amount of current that flows. Same with a MOSFET. Now, a regular bipolar junction transistor, BJT, is not a voltage controlled current source. It is a current controlled current source. The amount of current flowing from the base to the emitter, the amount of current flowing from the base to the emitter controls the amount of current flowing from the collector to the emitter. Not the case with a MOSFET. MOSFET's just like a vacuum tube. A voltage at the gate will control the current from the drain to the source. So in that sense, MOSFETs are very similar to vacuum tubes. And in fact, if we look at the characteristic curve of a MOSFET, and I'm going to compare this to a pentode in a minute, we have voltage from the drain to the source, and we have current through the drain. And each of these is going to be a different voltage from the gate to the source, and it's going to go up in value. And you know, I won't get into details, but you draw a load line depending on your design, and you have a quiescent point where the MOSFET is idling, and then when AC is applied, you just basically go up and down this load line, and you produce a sine wave. And if you look at the characteristics of a pentode, it's the same thing, except, you know, MOSFETs have a drain, a source, and a gate. Well, I'll draw, I'll say this. Instead of the voltage on a MOSFET, instead of the voltage on the drain, you have voltage on a gate. Voltage on a plate of a tube. So the plate of the tube is like the drain of a MOSFET. And instead of in the MOSFET you have current flowing through the drain, here you have current flowing through the plate. Same thing. And then instead of like a MOSFET where you had voltage gate to source, well, here you have voltage on the grid. So same thing, draw a load line, you have a Q point, and you're flowing up and down from that Q point. So again, MOSFETs, transistor equivalent to a pentode vacuum tube. And MOSFETs have advantages. Well, they have advantages over tubes because they can handle a hell of a lot more current than a tube, and they're faster than tubes. But they have advantages over BJTs, bipolar junction transistors. They're faster, they're less noisy, there's no thermal runaway. BJTs have to be compensated because as they heat up, they produce more current, and they can actually get into a runaway mode where they, you know, self-destruct. MOSFETs are not like that. MOSFETs have higher input impedance, generally lower power loss, can usually handle higher currents, and we just covered that their characteristics are more tube-like. So MOSFETs do have many advantages in an audio amplifier. Now, why am I talking about all this? Well, I'm only talking about all this because sound so damn good? And why does it sound so tube-like? Why is it so incredible? Well, the use of MOSFETs is part of it, but that Circuitron configuration must have something to do with it. Must. So, now, what I'm going to do is go through this schematic diagram very briefly, because this is way too technical, but I'm going to draw this out in block diagram form and show you how the amplifier works from beginning to end. This I'm going to be brief about. So again, I'm going to go through these technical schematics for about a minute, and then I'm going to redraw this in simplified form. But you have input signals. Okay, this is your audio signal, and basically, can't see it, but that goes down to there. Okay, you enter a first differential amp. These are differential amps. All they do is amplify the difference between the two inputs. So anything that's the same, okay, if you were to put in the same signal onto both sides, you'll get nothing out of this amp. Here are the outputs, by the way. Okay, you'll get nothing out of this amp. But whenever you have a difference in the signal, so let's say you have an unbalanced signal, so this one gets a sine wave and this one is just basically DC, it will amplify the difference between those two, and you'll get a signal out on one side and an inverted polarity signal out on the other side. So immediately you convert a signal to balanced. And one of the advantages of a differential amplifier, again, is, remember, it only amplifies the difference. So if somewhere in the course of either internal to the amp or maybe between your connectors, you introduce noise. Okay, so you have two connectors, right? One of them is usually one's your signal and one's a ground. Noise will be introduced to both sides, and because these wires are right next to each other, and be in the same amplitude and same phase. Well, guess what? If they're the same amplitude and the same phase, they're going to get canceled out by this differential amp. So that's one of the characteristics of diff amps, is they get rid of noise, and they also produce on both sides an inverted polarity, same version of the other one. So we go into a first diff amp, then we go into a second differential amp, and then there's two outputs from that differential amp right here. Inverted polarity, I'm just going to draw it like that, and then these are what feeds the final driver stage. Up here, this sets the bias right here. These are two little potentiometers that set the quiescent or the idling current. So first diff amp, second diff amp, here comes the signals, and okay, and this guy comes over. You can't see it because it goes off the page, but he will come over and come down to here. Okay, and then we have an inverted polarity right there. Here are the MOSFETs right here. So we have BJTs that drive the MOSFETs. Boom. And by the way, the speaker load, you can't see it, but it would be right there. That's what the speaker would be. Don't worry if this is too technical. I'm going to leave this in just a minute. That's what the speaker would be. Okay, so and this stuff in here, don't even worry about that. This is biasing, and this is in protection circuitry to ensure that the bridge is always balanced at quiescent or at idling. But these are the workhorses right here. These are the N-channel MOSFETs, and it's hard to tell. I had to study this for a while. I traced it out, and these are in the exact configuration that Yamaha says they are. Now, I won't get into that. Okay, so let me start out and redraw this schematic in something more manageable. So the signal comes in, goes to a first differential amp, okay, inverted phase, 2 of them come out, goes to a second differential amp. One side goes to this is the MOSFET, right, basically right here. One side of one polarity drives one MOSFET, and the other side drives this other MOSFET, and here's how they are configured if you trace the schematic. Just like Yamaha says, 2 separate circuits in a Circuitron configuration. Zooming in on the Circuitron that Yamaha uses, it looks just like this. I'm omitting all the protection circuitry and the bias circuitry here. So it's exactly what's going on, just like their diagram. You have one loop right here, and you have another loop right there. When these guys are idling and there's no AC, you can see that the power supply, positive DC, comes up to there, whatever value that is. Same thing, positive comes up to there, whatever value that is. Those two values equal each other, and you have no current flowing through the load. It's balanced. As soon as you get signal, one polarity is here, inverted polarity is there, then you unbalance the bridge and current starts to flow. So for example, and I think I covered this, but if you get a positive going, stop right there, you get some kind of positive value there, and at the same phase angle, you have a negative value down there, and you're going to have current flow in that direction, and so on and so forth. Current flow in the other direction. You have AC. The bridge becomes unbalanced. And one final drawing. Not that I need it, but just a little bit more detailed. Okay, this is the same thing we looked at. This is an overall block diagram of the schematic. Signal comes in, diff amp, to the drivers, to the MOSFETs. Okay, there they are. There's one MOSFET path, there's the other one right there. Okay, and then what that stuff was, I pointed out a little earlier in the middle. It actually has several inputs. It actually takes an input off a small resistive value, and it goes into this bias offset circuit. It does it from this side, and it takes some taps off the speakers too, and this controls the bias and the offset. It's basically a servo, and it makes damn sure that this bridge remains stable, that there's never any DC flowing through it. And the idle current adjustment, which is set at no load condition. So to set the idle current, you have no load on there, so you have an open circuit, and there's a couple of potentiometers that need to be set that basically control the idle current that is idling through this little servo loop right here, back around. Basically, I won't get into more detail than that. It's irrelevant anyway. But all right, so that is everything I wanted to discuss technical wise about the AS1100. Again, it's a Circuitron amp. I don't know, I know I said this in the earlier video, I don't know if anyone that's using this in a commercial, hobbyists like to build these things, but generally not a very commercially viable solution to an amp. Requires a lot of protection circuitry to make sure that that bridge stays balanced. It's very intricate stuff, but Yamaha's done it, and I believe there's a couple of aspects that make this amp sound so good, besides the fact that they're using quality components throughout, trying to find. I believe it's really 3 things that make this special in my mind, and this is just my personal belief. trying to find something here. There we go. Okay, so the things that make this amp special, number one, Circuitron, rarely used. Really cool, elegant, awesome way to amplify, to provide amplification. It's a bridge. Number two, the use of these power MOSFETs. These are great transistors. They're obviously doing an awesome job in this circuit. Well, really, those are the main things, but their feedback. Oh, you know what I mentioned? There is a feedback circuit, and it's very, very simple. Basically, the feedback loop taps off one on either side of the speaker, and they each go back to the very beginning of the signal path, and they feedback negative feedback on both sides of the first differential amplifier. It's that simple. There's nothing complicated about the feedback loop at all. But it's true what Yamaha says. There are two separate feedback loops, one for each circuit here, one for each side or of the Circuitron, and they feed back into their respective signal paths into the first differential amplifier. Really, really simple. And that's kind of what they have depicted right here. Okay, you can see the feedback comes down and then goes right in to the differential amplifier, and then this side comes right down. Exactly what the schematic shows. So all this makes the amp pretty special. It sounds great, and it's a unique, not unique design, but there's nothing else like it out there right now, and importantly, most importantly, it sounds fantastic. So their implementation of the Circuitron here is just on par. And that's really about all I want to talk about technical wise with the Yamaha. And I think in my next video, part 3, we're going to have it on the bench here and start looking at the rear panel and disassemble the quality, and you know, Yamaha's I'm very confident it's going to be just top notch. And then maybe try to figure out how much Class A power this thing is really delivering. And I said earlier I have a way, and I'll very briefly discuss that as the very last thing today. Okay. So back to the schematic. Okay, you see this, there's this little resistor right down here. It's basically bias resistor. It's 0.1 ohms. 0.1 ohms, very small. There's a tap right here, and this is tap right there. It goes up this path here, and then the other side of it goes up this path right here. I'm going to give you a close-up of it right here. Okay, here it is right there, and then this one goes up right there. Well, if you follow these all the way up to the top of the schematic, they end up going to a couple of test points, and I probably can't read that. It says idling. And when you adjust the idling current using a couple of potentiometers, FYI, earlier on in the second differential amplifier, it's these pots right here. You take a voltage reading between off of both sides of that 0.1 ohm, and I forget what voltage it's looking for, but it's I think it's 11 millivolts, and yeah, it is 11 millivolts, and well, 11 millivolts across that means 111 milliamps, 0.1 of an amp. That's where you set the idling, and that's what's basically flowing through that MOSFET when there's no load going through the bias circuitry. And well, so I was thinking, well, let's put a load on there, put a signal in, and start cranking it up and scope this, okay? Well, I should say, I'm just going to put a scope on this, and let's look at the signal. And when this MOSFET on this side is in class A, we should see across that little resistor a sine wave. And when this MOSFET starts entering into class B, remember class B is when one transistor will output one half of the sine wave and the other half, push-pull so to speak, we should start seeing that. So by cranking up the input voltage to get enough power across the speaker load, at some point, if this is a class B amp, at some point we should start seeing, you know, that classic class B push-pull half cycle sine wave. And the question is, at what power on the output across the speaker load, at what power does that start happening? And that's what I want to do. I want to find out how much class A power I'm getting. So just out of curiosity, because this might be the other thing that explains why this amp sounds so good. Maybe it's heavily biased into class A and it stays class A for a long time. And again, through my clip speakers, I hardly ever get past 1/10 of a watt, and so I'm probably listening to it in class A the whole time. So I want to find out if possible, and this test point is readily accessible. I don't want to disassemble the circuit boards of my amp. It costs too damn much, and I don't want to screw something up. But because that test point is accessible, I thought I'd give that a try. So that might be fun. So that'll be in the next video or the one after that. But that's enough for this technical explanation today. Look forward to part 3 where we have the amp on the bench. Cheers, thanks for watching. Bye-bye.